Alright, welcome. In this video we're going to be talking about graphs of radical equations. And if you're looking for how to solve radical inequalities, I'm going to record that in a separate video. That'll just be in the next video. Okay, we're going to start with graphing y equals the square root of x. Okay, and so just like, in Algebra 1 or whenever you first learned about how to graph, we're going to start by making a table, plotting points, and connecting dots. But you don't need me. See me dig up some paper and make a t-chart. Okay, I'm going to plug in x equals 0, 1, 4, and 9, because these are numbers I know how to take the square root of and get an integer back, and I'll be able to actually plot on grid points. So the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, and the square root of 9 is 3. So I'm going to go in here and I'm going to plot the point 0, 0, 1, 1, 4, 2, and 9, 3. And then I'm going to connect the dots, having just, plotted points. So this strategy of make a table, plot points, connect the dots, this is still valid. This is something we will use more in this class, okay, when we're first learning about a new function type. Okay, now, I think what I would normally ask in class is like, hey, does this look familiar to anybody? Does this look like anything you've ever seen? And usually people sit there for a second, and then somebody's like, oh, wait a second, this is not all of it, but it looks like part of a parabola that got turned on its side. And that's exactly what it is. And we know a parabola is, represents something like y equals x squared. And what I would propose is if you squared both sides of this equation, you'd get x equals y squared. And, well, I just say that, there's more to that that we're not going to be talking about today. But let's discuss the graph of y equals the negative square root of x. All right, well, this should be pretty similar to what we did before, right? Because all that happened was we just multiplied this square root by -1. So really, y became negative. So I'm saying -0, well, that's 0. -1, -2, and -3. Okay, and so now I'm going to plot 0, 0. I'm going to plot 1, -1, which for x is 1, and y is -1. Then I'm going to plot 4, -2, and 9, -3. Because remember that when we see the square root symbol, that means the positive square root. So if y is the negative of the positive square root of x, that's why we're seeing negative y's here on this graph. Okay, it looks like I kind of missed it a little bit, but it'll be all right. Okay, and that's the kind of the other half of that parabola. Okay, that sideways parabola. Now, the graph of y equals the square root of negative x. Okay, maybe up until recently you've been like, that's kind of a bad news function, right? It's going to keep having me take the square root of a negative number. But if you think about what would happen if we plugged in negative values of x, we could get real numbers back for y. So let me bring in my table here. All right, so I kind of went back in and cleared it out and took it back to kind of like y equals the positive square root of x. But we've now got a negative x on the inside. So that's going to affect what kind of x's I'm allowed to plug in, right? Before, I was thinking, okay, well, if I plug in a negative number for x, I'm not going to get a real number back, say over here. And that's why we saw no graph to the left of the y-axis. Okay, over here, this is going to be a little different. I have to be a little more intentional, okay? I can still take the square root of -0 because -0 is 0, and we know the square root of 0 is 0. But 1, if I plug in 1, I'll be taking the square root of -1, and I get I, and there's really no place on the x, y plane for values of I. So what we're going to do instead is we're going to say, all right, if this was -1, if x was -1, I'd plug it back in there, and I'd be taking the square root of +1, and so I'd get +1 there. And then if I plugged in -4 and -9, I could make those positive by multiplying by -1 first, and then take the square root, and then I would be seeing +2 and +3. So 0, 0, -1, 1, -4, 2, and -9, 3. And that's telling me that we've got ourselves one of these sideways parabolas, except it's going to the left. That'll be that way for y'all. And so I'm going to go over here, and I'm going to just really kind of be a little more careful this time. I don't know, my sketches have not been great today, but I think that one's going to be the worst of all. I think there's something going on here. Yeah, that needs to be a little bit more like that. That'll do. Okay, so it's got this, like it increases and then it levels off type behavior. Or you can look at it as a sideways parabola, however you want. Okay, so these are some pretty introductory square root graphs. All right, now let's look at the graph of y equals cube root x. So I'm going to do the same thing. I'm going to make a table, plot points, and connect dots. Okay, so I'm going to have some x values. I'm not just going to go like -8, -7, -6, -5, all the way through 6, 7, and 8. That's not going to be the way for us to go. We need to be a little more strategic about what values of x we're plugging in, thinking about things that I can actually take the cube root of, which there aren't that many. So that'll kind of limit our level of responsibility. So y is equal to the positive cube root of x. Okay. And, okay, so I need to make this into a table. Think about what kind of numbers am I good at taking the cube root of? Okay, I'm definitely good at taking the cube root of 0. Cube root of 0 is 0. Cube root of 1 is 1, because any power of 1 is 1. Okay, so I've got 2 points. Then the next number I know how to take the cube root of is positive 8. That's why the graph goes up to 8 in x. Okay, the cube root of 8 is 2. Right, and you can't see it, but I just plotted the point 8, 2. All right, then, but I think hopefully, so far in this unit, you've seen that we're okay with taking the cube root of a negative number. That's fine, it just comes back negative. So I could also be ready to take the cube roots of -1 and -8, and then I get -1 and -2. Okay. -1 being the cube root of -1, because if I cube -1, I get -1. And -2 being the cube root of -8, because if I cube -2, I will get -8. All right. And then plotting these points. And then I'm going to connect the dots. And hopefully this one looks a little familiar to you. I'm just going to point out to you that the spot here at the origin, kind of what I'll call the center of the graph, the graph is going to go vertical momentarily. Now, it's not going to really be vertical except for at one point, otherwise it wouldn't be a function. But that's kind of just the AP calculus teacher in me telling you about one of the important aspects of the graph of y equals cube root x is this momentary verticality. And we'll have a lot more to say about that in terms of the slopes of this function and everything in a couple of years once you're in my calculus class. But here we've got ourselves the graph of y equals cube root x. Okay, so kind of first things you're probably noticing is that, hey, it extends in both directions. That's going to be true in general. Also, it kind of looks like the graph of a third degree polynomial turned on its side, except it also looks like it got flipped over somehow, and that's going to have to do with there's more there. Like I said before, there's more there that has to do with the relationship between a function and its inverse that we will talk about in this class. We're just not going to talk about it right now. We're just kind of sketching some graphs right now. So I think the next one's going to be, negative cube root of x, which I might point out is the same as the cube root of negative x. I'll let you think about why that's true. But if I was to go over here and just change this to the negative cube root of x, I'm just going to take all of these y's and multiply them by -1. -0, 0, negative, negative. Okay, multiply -1 and -2 by -1 and get positive. Okay, so kind of like before, we're just going to see this thing flip. Okay, it's going to be upside down. All of the negative y's became positive y's. All the positive y's became negative y's. Okay, so I'm going to plot 0, 0, 1, -1. You can't even see my table. 1, -1. 8, -2, -1, +1, and -8, +2. And I'm going to connect these dots, and hopefully I'm going to have success, and I'm going to draw a really nice graph. But even if I don't, it's not a big deal, right? It's just a sketch. If we want a really, really accurate graph of this thing, we're going to go, open up a browser window, go to desmos.com, pull out our graphing calculator, any of the many, recourses we have for producing high-quality graphs. That wasn't great. Okay, I did the best I got. All right, now, the domain of a radical function. I feel like, hold on, let me think about if there's anything more I was going to say about that before I move on to the domain discussion. Well, there was something more I had intended to say. I'm not remembering what it would be, so I'm just going to move on to the domain discussion. But I think it would probably be good for me to remind you of what we mean by domain. All right, so the domain of a function f of x is going to be the set of x values that I would be able to plug into f and get a real number back. And I know there's discussion about domain in Algebra 1, but it's kind of like without any sort of thread. It's kind of dictated by context, right? That struggling to think of an example right now because I'm for 1 this year, but But I know that those situations, the domain questions there are dictated by context. For us, it's like really the threat of taking the square root of a negative number, or dividing by 0, or eventually, I think in the next unit, taking the log of a number that isn't positive. These are the things that can go bad, and so these are things we have to be aware of in the domain discussion. This will be something we'll be doing a lot in this class, really, for the rest of the year. Okay, so if n is even, if we're taking an nth root, then what we put on the inside of the radical, the radicand, has to be greater than or equal to 0. So this thing x, I'm going to grab it, and I'm going to set greater than or equal to 0. Equal to 0 is okay because I can take the square root of 0, I can take the fourth root of 0, I can take the, any even root of 0, and I'm just going to get 0. Okay, and I can take, square root, fourth root, 12th root of a positive number and get a real number back. But if I take the 4th root, 12th root, 20th root of a negative number, I'm going to get an imaginary number back, and that would not be a real number. Okay. So what we do is we grab the inside of the radical, what we would call the radicand, and we set it greater than or equal to 0. Okay. If I went back and showed you, these, actually maybe I'll do that here in a second. If n is odd, like a cube root or a fifth root or whatever, the domain is going to be all real numbers, because we can take the cube root of a negative number, we can take the cube root of a positive number, we can take the cube root of anything we like, and we're going to get something back. Okay, so if you see like cube root and you get a domain, well, that's really easy. We just always say all real numbers because we can put anything we want into a cube root. Okay. Yeah, and so thinking about the graphs that we've already produced, okay, I'm seeing this graph is going forever in both directions. If you can think of an x, there's going to be a value of y that corresponds to it on this graph and on this graph. That's where we say the domain is all real numbers, because we can plug in anything we want. We're going to see some graph there. Okay. Whereas over here on the front page, okay, y equals square root x, if we were going to talk about the domain of this thing, I would take the inside of the radical, the radicand, and I would set it greater than or equal to 0. So I'd say maybe, some purple, x greater than or equal to 0. It doesn't really look purple when I write it on top of a highlighter, but that's okay. Okay, over here, same radicand, just an x on the inside of the radical, same domain. Okay, the graph itself looked different, but the set of x's that I'm allowed to plug in are all x's that are greater than or equal to 0. Where that switched was down here, where I started manipulating what happened, on the inside of the radical. So to find the domain of this thing, I would grab the radicand, and I would set it greater than or equal to 0. And so that would be negative x is greater than or equal to 0, but that doesn't look quite right. We might like to either add an x to both sides or multiply both sides by -1 to just get at x. And either way, that will reverse the direction of our inequality, and we'll get x is less than or equal to 0, which is exactly what we're seeing over here. Now, if we're wanting to find the domain of a function like, one of these, what we're going to do, same thing. We're going to, if it's square root or a fourth root. Now, this class, we're really concerned mainly with square roots and cube roots, but, there's going to be the occasional fourth root or fifth root in here. For a square root, we're going to take the inside of the radical, the radicand. We're going to set it greater than or equal to 0, and then we're going to solve. Okay, we're pretty experienced in solving this type of inequality right here. We're going to add 3 to both sides, and that'll be my domain. Okay, for this one, we're going to do the same thing. We're going to set it greater than or equal to 0 because it's a square root. So 4x plus 40 is greater than or equal to 0. 4x greater than or equal to -40. I divide both sides by 4, and I get x is greater than or equal to -10. Okay, for h of x equals the cube root of 1 minus x, this is a cube root. We can plug anything we want into cube root. Okay, there's no like, oh, you can't take the cube root of a negative number. Yes, you can, and you take the cube root of a negative number, and it's going to come back negative. So I'm just going to say that the domain of this one is all real numbers, which is what we're going to say anytime we're saying a cube root. Okay. Is there discussion on range here? All right, so just to remind you, the range is the set of actual outputs achieved by the function. Okay. So if I plug a number into square root and I get a real number back, I can say this is, this is square root of x. Okay, what we said last time, or maybe probably not last time, 2 times ago, when we were talking about the definition of square root of x, is it's the positive square root. So remember that the square root is greater than or equal to 0. Okay, and now we'll have more interesting functions than this, but if you think about the y values that came back with y equals square root x, in fact, maybe I'll just draw you a picture of y equals square root x. It looks like that. Okay, we see x's are greater than or equal to 0, y's are also greater than or equal to 0. And for cube root, see, it's not growing fast at all. It's really leveled off, but it is going up as we move to the right, and is going down as we move to the left. So this is going to hit all of the y values, and this is going to have range, all real numbers as well. That was kind of what made me think of it, is that, kind of in this example down here, they ask you for domain and range of a cube root function. Very easy, all real numbers, all real numbers. Okay, don't forget that. All right, now let's produce some actual sketches of graphs of radical functions. Now, these are pretty okay, but I'm going to do a couple more at the end that have like a little bit more going on with them. Because I think that I've worked the tests, and I feel like there might be on there where you got a little more going on than these. Okay, so square root of x plus 5. That's a situation we have not dealt with, but we already have, if I went and dug up I can feel them under here, little post-it notes for my graph of y equals the square root of x. Making this square root of positive x again. If I just made this the square root of x and then added 5 on the outside, well, I just 0 plus 5, 1 plus 5, 2 plus 5, 3 plus 5. So it's the same shape, just moved up by 5. Okay. So I'm going to say, all right, okay, standard y equals square root x starts at the origin and increases and levels off. So this one's going to start at 5, increase, and level off. Okay. If you needed another point because you were on a grid or something, or you say the instructions told you needed another point, you just pull probably any number that we know how to take the square root of. So maybe I'll say that this is 1, and then the y coordinate there would be the square root of 1 plus 5. That'll be 6. Okay, that would be a decent sketch. Okay, if I wanted to find the domain and range of these characters, I'm thinking, okay, well, domain, you take the radicand and you set it greater than or equal to 0. Okay, x is greater than or equal to 0. We're seeing that there. For the range, we could kind of like try to figure it out based on the graph, but I actually think it's easier to think about it numerically. Y is equal to square root of x plus 5. The very least that square root of x can be is 0. So the very least that y could be would be 0 plus 5. And so I'm saying y is greater than or equal to 5. Okay. We're also seeing that on the graph. And it probably would have been good to label my y-intercept there. So I had 2 labeled points. There we go. Okay, for the square root of x plus 3, this is something that's different for us. Maybe I'll start with the domain discussion, right? Because I've got something weird going on the inside. X plus 3 on the inside of a square root. So for the domain, I'm thinking I'm going to grab this x plus 3. I'm going to set it greater than or equal to 0. We've already solved this inequality once in this video. X is greater than or equal to negative 3. Okay, well, all of these square root functions, their domain just ends at a spot. Or you could look at it as it begins at a spot. Okay, and that's what we're seeing right here. We're seeing the edge of the graph. Okay, so I know that the graph is going to start at x equals negative 3, and it's going to go to the right of that because x is always greater than or equal to negative 3 in the domain. So I can go over here, and I'm just going to say, all right, this is the positive square root. So I know it's going to start somewhere, and it's going to increase and level off, just like that. Okay. Now we've determined that this is at x equals negative 3, right? Because x is greater than or equal to negative 3, x equals negative 3 at the very edge of the domain. What is the y coordinate at the edge of the domain? Well, this is y that corresponds to x equaling negative 3, so it's y equals the square root of 0, square root of 0, 0, so I've got negative 3, 0. Okay. Which means if it's negative 3, 0, I'm sitting on the x-axis, y is equal to 0 there. And I'll draw an x-axis. Okay. I feel like it makes sense for me to plug in, or to draw a y-axis, and that'll give me a y-intercept. Okay, a y-axis will be to the right of x equals negative 3, so I don't know, maybe it's like here or something. Doesn't really matter. It's your world, draw it however you want. Okay, and then I might label the y-intercept, but if you wanted to label the point where x was equal to 1 or something, you could do that. Right? Doesn't matter. So the y-intercept is going to be y equals the square root of 0 plus 3 is the square root of 3. Okay. Now, these next two, okay, these are just kind of like multiplied versions of y equals square root x. So, okay, if it's 6 times as large, right? The quantity of that y represents 6 times as large as the quantity that square root x represents, it's going to look the same. It's just going to go up higher on the scale, right? So it's going to be like that or something. But maybe we label that as 1. When I plug in x equals 1, I'm taking 6 times the square root of 1. That would be 6. Okay, yeah, something like that. Okay, just something to indicate that this thing is taller. It's growing faster at first. I don't know, however you want to say it. Use your own words. Okay, but I'm not going to ask you to describe the difference. I'm just going to ask you to sketch the graph. All right, -2 square root of x. Okay, this is a negative square root of x is going to open down, or like upside down. It's going to be an upside down one of these. So it's going to decrease and then level off. So, but my domain is still going to be just like x is greater than or equal to 0. I'm not adding anything on the outside. This is pretty much just going to be like y equals square root of x, upside down and twice as tall. So I do that. And who knows, maybe I'll make this, label x equals 4. -2 times the square root of 4 would be -2 times 2 is -4 down here. I don't know, it looks kind of believable. Okay, now this has got more going on here. I should probably solve for the domain. Okay. So I'm going to go over here and I'm going to grab the radicand and I'm going to set it greater than or equal to 0 for the domain. Okay, I'm going to solve for x. I'm going to multiply both sides by -1, which will reverse the direction of the inequality. And I get x is less than or equal to -1. Okay, so that's a piece of evidence that tells me that this thing needs to be going backwards, kind of, or backwards to our frame of reference. Also, that -x on the inside of the square root can be telling us that the thing needs to go back to the left. Okay. Either way, depends on how you want to look at it. Okay, then the range is still just a square root, so it's going to be y is greater than or equal to 0. Because the square root itself, it's the positive square root, and at the very least, it's going to be taking the square root of 0 if x is, say, equal to -1. You can see that. All right, so if x is equal to -1, I'm taking the square root of 0, and that's 0. So, maybe I'll say that's -1. And it's going to open back to the left because all of the x's that comprise this graph, it's where x is less than or equal to -1. And if you needed to plot, like make a table, plot points, and connect the dots, there's no shame in that. I'm just kind of trying to use my reasoning skills to plot a graph. Okay, the y-axis is going to be to the right of x equals -1. Put that there. If I needed to plot another point, well, might choose -2. Wait, is that going to work? -2, +2, -1 is 1. Yeah, okay, yeah. So, there, I've got myself a second point. All right, now 1 minus the square root of x. Okay, the domain of this thing is just going to be x is greater than or equal to 0. But the y-coordinate of the beginning of the graph is going to be, okay, well, that means domain x greater than or equal to 0. The y-coordinate is equal to 1 minus the square root of 0, so y is going to equal 1. So this graph starts at x equals 0 and y equals 1. And then it's the negative square root of x, so it's going to go down. Okay. Or you could think about, at the very least, this is 0, right? Usually, square root of x is bigger than 0. It's going to be a positive number. Okay. I can take 1 minus a positive number, or I can take 1 minus 0. Okay, so 1 minus 0 would be actually the maximum that this function could ever achieve. And then it's going to decrease the bigger x gets, the more I'm subtracting from 1. So I'm going to go over here. I might as well solve for that x-intercept. I can see that there's an x-intercept. Maybe I can solve for it, right? So what I'm going to do, I'm going to go over here, and I'm going to say, okay, an x-intercept, that's where y is equal to 0. Okay. And so I'm going to say 0 equals 1 minus the square root of x. I'm thinking this is an equation we can probably solve with our eyes, right? Okay, we can say I need to plug in x equals 1 in order for this equation to be true, so I've got my x-intercept, and there I go. Okay, on the homework and on the quiz and tests and stuff, they are going to ask you for x and y intercepts of these things, but that's something that we have practiced so much in this class that I'm not going to waste a whole bunch of time on the video solving for x intercepts and y intercepts. Now, on the last page, yes, this video is getting a little long. There's been a lot of graphing, but I know there's supposed to be some cube roots back here, so yeah, I'm going to do that. I'm probably just going to like run through the next 3, just real quickly show you what happens to the 3 after that, and then do a couple of examples and get you practicing on your own. Okay, so the cube root of x minus 1. What I'm going to do, okay, this thing has domain and range, all real numbers. So what I might do instead is kind of find the center of the graph. Okay, the center of the graph is going to happen where I'm taking the cube root of 0. I really kind of did the same thing. It wouldn't be the center of the graph, it would be the beginning of the graph, or the end of the graph when I was solving for the domain on a square root function. But over here, I'm going to say, all right, the thing on the inside needs to equal 0. So I grab that x minus 1, I set it equals 0, I solve, I get x equals 1. Okay, y is equal to the cube root of 1 minus 1, which would be equal to 0. So the center is at x equals 1 and y equals 0. And then it's the positive cube root, so we know what that looks like. It's kind of like an S, kind of. There's a different function that has an S shape we'll be quite a bit more interested in than this at a later time. I don't think in this course, but so I'm just going to draw this cube root shape, give it some arrows. If I got to, give another point, I'll do that. Okay. Yeah, and this might fit with discussion of y-intercept. All right, and just to remind you, because it's been a while, a y-intercept right there, that's where x is equal to 0. Okay, so I'm going to say y equals the cube root of 0 minus 1. And the cube root of negative 1 is negative 1. Okay, so I'm seeing that down here. Whoops, that didn't quite right. But there I've got myself a sketch of the graph. Okay, cube root of x minus 1. Okay, so for this one, I'm going to do the exact same thing. I'm going to find the center. Okay, the center is going to be where x equals 0. But for a cube root, I grab the inside of the radical. I set it equal to 0. And then, okay, the y-coordinate will equal the cube root of 0 minus 1. Okay, so I've got the same, y-intercept, but that does not mean that the graph is going to look the same. Okay, that would be a really common error distributing the cube root over x and the negative 1, but it doesn't work like that. Unfortunately, you can't distribute radical over addition or subtraction. It just wouldn't work. And all sorts of other problems that we don't want to. Okay, so I go over here on the y-axis, 0, negative 1 is going to be the center of my graph. Okay, but otherwise it looks the same. So this is where it went momentarily vertical. So it's going to go over here. That one was pretty good. I think that's the best one I've produced yet on this video. But I still have hope that I've got better still to come. Okay, that's going to be equal to 1, yeah, because the cube root of 1 minus 1 is going to be 0. This is over here at negative 1. We already found that. That's going to be a good sketch. Okay, negative 2 cube root of x plus 3. Okay, so it's going to start at 3, and then it's going to be kind of an upside down cube root. The bigger x gets, the more I'm going to subtract from 3. Okay, but again, the center is going to happen where x is equal to 0. So we've got 3 here. Negative 2 cube roots means it's going to be kind of upside down and a little bigger vertically. So okay, so I've got myself a graph there. That's 3. Maybe we're looking pretty zoomed in, and I'm just going to be showing the x-intercept there. Okay, if you had to plot 2 points, what I'd do is I'd go over here. I'd say this is 1. I'd say, all right, negative 2 times the cube root of 1 is negative 2 plus 3. Okay, that would be 1. Okay, this figure's definitely not drawn to scale, but there you go. That's what I've got. Okay, y equals x to the 2/3. Y equals x to the 1/3 is the cube root of x. So this is the cube root of x. squared. Okay, so this was really kind of just like a thought exercise for the people in my class. We're not going to be graphing y equals x to the 2/3. I kind of just like this one because it's one to think about. And it kind of looks like the graph of y equals the cube root of x, except it's always positive, right? Because this is equal to the square of a number, which could be negative, could be positive. So it's kind of like cube root x. Okay, when x is positive, it does look more or less the same. But when x is negative, it's kind of becoming positive. And so what will happen is, right, because I'll take the cube root of a negative number, that's negative, and I square it, it's positive again. So it kind of comes back over here. It kind of looks like a bird, okay, if you're feeling creative. But that's just a different looking graph that is kind of like right at our level right now. All right, since I've already over half an hour, I'm going to just kind of show you what this is, what's going on with these, and then I'm going to work one that's got a little more detail in it, and then I'll set you loose. Okay, looks like the square root of x minus 6. Okay, so we saw when we were studying polynomials that the graph of, you say y equals x to the 4th, looked a whole lot like y equals x squared. It's just a little more extreme in the middle. And so what's going to happen here is the same thing. So this would start at x equals 6, right? Because x minus 6, do my domain over here, greater than or equal to 0 because the index of the radical is even. Okay, so the graph kind of starts over here at 6. Otherwise, it looks the same. Okay, and yeah, actually, I like that sketch a lot. I'm gonna just leave it there. And then the 5th root of x might as well be the cube root of x, right? The only differences between the 5th root of x's graph and the cube root of x's graph would be kind of the same differences between the graph of y equals x cubed and the graph of y equals x to the 5th. And if you're sitting there thinking, I thought they had pretty much the same graph, then to you, cube root and 5th root will have pretty much the same graph. All right, so let's do one with like kind of all the pieces to it. So like let's find the domain, the range, the x-intercept, the y-intercept, and sketch the graph of this function f of x. Okay, I kind of like to start with the domain because that lets me know where to start because it's a square root function. Okay, if this is a cube root function, we'd say, okay, domain all real numbers, range all real numbers, easy, take our credit, move on. This is square root, so we're going to have to be a little more careful. So the domain, we're going to take the inside of the radical, the radicand, we're going to set that greater than or equal to 0. And then I'm going to solve. Great, we're happy there. Okay, now this is the edge of my domain is x equals 4. So if I want to compute the range, let's see. The range is going to be, okay, well, at the very least, I'm adding 0 to negative 3. If this was a minus, I'd say I'm subtracting at the most, I'm subtracting at least 0, right? Because, the square root is at least 0. It's been a while since I've talked through these problems. Okay, so this is at 3 plus at least 0. Suppose it could be 3 minus at least 0. Okay, so but 3 plus at least 0 means that y is going to be at least 3. Okay, telling us what's going on here. That was not what was supposed to happen. Oh, yeah, okay, so it's supposed to be over here, negative 3. Yes, I wanted this to happen. This is exactly what I wanted. Yeah, because we're going to go for the x-intercept and the y-intercept. And I don't know if I remember any of these working out this way with the y-intercept. Okay, so the next kind of thing would be, x-intercept, y-intercept. Okay. So x-intercept, that's where y is equal to 0. So I'm going to go over here and I'm going to say 0 equals negative 3 plus that square root of 4x minus 16. Okay, I'm going to add 3 over here. I'm going to square both sides. Now I will be needing to check my solution at the end, but this is not really looking like the type of equation that we ran into in the last lesson that caused us to get extraneous solutions. I'm going to add 16. Divide by 4. I've got myself an x-intercept. Okay, 25 over 4 times 4 would be 25 minus 16 is 9. Square root of 9 minus 3. Yeah, okay, that's working. I'm going to get y equals 0. For the y-intercept, that's where x is equal to 0. Still in my shot. Oh, yeah, plenty of room. So that's x equals 0. And y will equal negative 3 plus the square root of 4 times 0 minus 16. And while we know that this is negative 3 plus 4i, that is not a real number. And so there is not a y-intercept. So no y-intercept. But we could have also seen that that was going to happen if we looked over here and saw that the domain of the function was where x is greater than or equal to 4. X equals 0 is not in the domain. I'm not allowed to plug that in because if I plugged it in, I don't get a real number back. Okay, so there is no y-intercept. Okay, and you might go, how can a graph not have a y-intercept? Well, let's just go ahead and draw this. Okay, I need the point 4, negative 3. So that's in the fourth quadrant. I'm going to definitely favor the first and fourth quadrants in my sketch here. All right, so I'm just going to decide that this is going to be 4, and that's going to be negative 3. Okay, that's the edge of my domain, so I'm going to be, okay, that's the dot there. But this is a negative 3 plus a positive square root of x, so it's going to do that increase and leveling off thing right here. So I'm just going to kind of draw the graph best I know how. And, you know, the scale might be a little off or something. But in general, this is going to be a pretty good sketch. We've already computed the x-coordinate of the x-intercept. That's 25/4. I might as well write that in there. What would that be? That's, well, bigger than 6. 6 1/4. I don't know. Who knows? Maybe that is actually right. And we've got ourselves a graph. Yeah, notice that this graph does not hit the y-axis, therefore there's no y-intercept. I think that's all I've got to say. That's all the examples I want to do in this video. Thanks for watching. Thanks for being here. Hope it helped.